Okay, welcome back. So in this problem 3.2b, we have already completed the first two sections. We've got parts A and B have been completed in a previous video. Now we're going to pick up right here and begin this computation of the variance. Now, the variance starts to get a little bit slow and tedious in the calculations just because of the nature of the formula that we need to use. So what we're going to look at here for the variance, so the notation that we're going to be using, this is a sample variance, right? This is just a sample of 10 EU countries. So it's a sample variance, and so this is S squared. And we'll come back to this, the fact that it's squared a little bit later on. We'll see what happens when we eliminate that square. But for now, our variance, this is S squared. And what we're going to be doing, we first need to calculate all of the differences between individual observations and the mean. So our mean is given to us, this is here 7.6. These individual observations, xi, those are each of these observations in this data set. So we're going to be doing 10 differences because I have 10 observations. And then once we've got those differences, we're going to square each of them, and then we're going to add them all together. So we're going to sum across I equals 1, so that's this first observation here, through to n, which is, in this case, 10. So then we're going to add all of those squared differences, all of them together. And then finally we divide by n minus 1 to get the variance. Okay, so the first thing that I'm going to do, let me just, where's my cursor here? Let's calculate all of these squared differences first. So I'm going to put in just as a header. So this is going to be these differences, and we're going to square them. So I'm going to go through from 1 down to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we're going to add all of those up. And down here, when we add all of those square differences together, what will be in that box will be our numerator up here. Okay, so let's get started, as this can take a little bit of time. So the first one that I'm going to work with, I'm going to start at the 5.6, and I'm going to work down the data set here, always using this mean. Okay, that value doesn't change. That's what we're going to be putting in here. Okay, so let's begin. I'll get my calculator. So the first observation is 5.6 minus that mean, 7.6 equals, so negative 2, and then I'm going to square that, and I have a value 4. So the first value here is 4. And now we have to carry on, only 9 more times. 5.8 minus 7.6 equals, square it, 3.24, and on and on. This is what I mean why it can get a little bit tedious. 7.6, 289, and the problem with this tediousness really is that it's really easy to make silly, simple mistakes just because you're doing basic calculations, but so many of them and repeating that it can be really easy to press a wrong button, to skip an observation, anything like that can happen, and it will inevitably result in the wrong answer. So just take your time, as long as you've got time to spare on an exam or whatever you're working on. Okay, I'm at 6.7 here. 6.7 minus 7.6, 81. So while I can do that one in my head, that one's going to be 0. Eight. Where are we? 16, sum on number 7, 8.3 times, 8.3 minus 7.6 squared, so 0.49. And this one I've got twice, so I can just skip. Poland and Denmark are the same. And now we just have two more. Germany, 9.1. Two and a quarter. And finally, Greece, or Netherlands, 11 minus 7.6. 1156. Okay, so what we've got here now are all of these squared differences. So we've calculated what's in the yellow rectangle. Now we're going to add all of those together, and that will give us our numerator. So if I start at the top, 4 plus 3.24 plus 289 plus 0.81 plus 0 plus 0.16 plus 0.49 twice plus 2.25 and 11.56. So 2589. So that's our numerator, 2589, divided by n minus 1, that's 10 minus 1. And so, last step, divide by 9, let's call it 2.9. Let's keep it simple here, 2.9. So finally, there's our variance. So, what is this good for? Well, on its own, not a lot. This gives us it's a measure of the variability of the data set, but on its own it can be hard to interpret for a couple of reasons. One, in terms of its magnitude, a larger number means greater amount of variability relative to a smaller number. But still, in terms of its magnitude, it's more useful when you can compare it against other measures of variance. So if I had, here I have a sample of per capita emissions for EU countries. If I had another sample from, say, North America or Africa or Asia, and I had a variance for those countries' CO2 emissions, well, then I could compare them and I could see which region of the world has greater variability among its countries. Another problem with the variance is that the units of measure are in these units but squared. So this would be 2.9 metric tons of CO2 per capita squared. Hard to really wrap your head around exactly what that means, to square those units. Sometimes, if it's squared centimeters, well, we can understand what that is, but squared per capita, it's harder to really grasp. So that actually brings us to the next part D, which is the standard deviation. And the standard deviation, well, the notation for that is, wouldn't you know it, this is just S. And so it's entirely related to our variance, and that the standard deviation is just the square root of the variance. So the calculations now become much simpler. Once we've done all that work getting the variance, now all I have to do is take the square root of that, and I have 1.7 is my standard deviation. So 1.7, this is now measured in the same units as my data. So 1.7 metric tons of CO2 per capita. It's not squared anymore. So again, this is a measure of the spread. On its own, still tough to use because it's primarily useful for comparison across similar data sets. I say similar because if we're looking at this similar data set, so data sets that are not entirely the same, so if I'm looking at CO2 per capita emissions, and let's say I'm comparing it against obesity levels or something like this, just some totally different variable that's not related, and I want to see which of these two variables shows greater volatility, greater variance, well, then it might be useful to use this next one, which is the coefficient of variation. Now this allows us to compare between data sets that have very different means and also very different standard deviations. And the coefficient of variation, I don't have a notation for it, so let's just call it coefficient var. This is just the standard deviation divided by the sample mean and times 100, so that we can speak in terms of a percentage. So it's the standard deviation as a percentage of the sample mean. And so if I fill in my numbers, this is 1.7 divided by our mean, still our same mean over here, 7.6 times 100. Let me get my calculator. 1.7 divided by 7.6 times 100. Oops. Oh, something went wrong there. 1.7 divided by 7.6 times 100. So 22, let's say 24%. 22.4, I think. 22.4%. So my standard deviation is 22.4% of my mean. So again, useful for comparing across data sets to identify which data set shows the greatest dispersion or the greatest amount of variability. Okay, so that finishes up for 3.2 question B on our measures of variability. I hope this has been helpful. Thanks.